a buck converter is a voltage step-down and current step-up converter. The simplest way to reduce the voltage of a DC supply is to use a linear regulator, but linear regulators waste energy as they operate by dissipating excess power as heat. Buck converters, on the other hand, can be remarkably efficient, making them useful for tasks such as converting the main voltage in a computer down to the 0.8-1.8 volts needed by the processor. Theory of operation. The basic operation of the buck converter has the current in an inductor controlled by two switches. In the idealized converter, all the components are considered to be perfect. Specifically, the switch and the diode have zero voltage drop when on and zero current flow when off, and the inductor has zero series resistance. Further, it is assumed that the input and output voltages do not change over the course of a cycle. Concept. The conceptual model of the buck converter is best understood in terms of the relation between current and voltage of the inductor. Beginning with the switch open, the current in the circuit is zero. When the switch is first closed, the current will begin to increase, and the inductor will produce an opposing voltage across its terminals in response to the changing current. This voltage drop counteracts the voltage of the source and therefore reduces the net voltage across the load. Over time, the rate of change of current decreases, and the voltage across the inductor also then decreases, increasing the voltage at the load. During this time, the inductor is storing energy in the form of a magnetic field. If the switch is opened while the current is still changing, then there will always be a voltage drop across the inductor, so the net voltage at the load will always be less than the input voltage source. When the switch is opened again, the voltage source will be removed from the circuit, and the current will decrease. The changing current will produce a change in voltage across the inductor, now aiding the source voltage. The stored energy in the inductor's magnetic field supports current flow through the load. During this time, the inductor is discharging its stored energy into the rest of the circuit. If the switch is closed again before the inductor fully discharges, the voltage at the load will always be greater than zero. Continuous mode. A buck converter operates in continuous mode if the current through the inductor never falls to zero during the commutation cycle. In this mode, the operating principle is described by the plots in Figure 4. When the switch pictured above is closed, the voltage across the inductor is. The current through the inductor rises linearly. As the diode is reverse biased by the voltage source V, no current flows through it. When the switch is opened, the diode is forward biased. The voltage across the inductor is. Current IL decreases. The energy stored in inductor L is. Therefore, it can be seen that the energy stored in L increases during on time and then decreases during the off state. L is used to transfer energy from the input to the output of the converter. The rate of change of IL can be calculated from with VIL equal to during the on state and to during the off state. Therefore, the increase in current during the on state is given by. Conversely, the decrease in current during the off state is given by. If we assume that the converter operates in steady state, the energy stored in each component at the end of a commutation cycle T is equal to that at the beginning of the cycle. That means that the current IL is the same at T equals 0 and at T equals T. So we can write from the above equations. The above integrations can be done graphically, in Figure 4, is proportional to the area of the yellow surface, and to the area of the orange surface, as these surfaces are defined by the inductor voltage curve. As these surfaces are simple rectangles, their areas can be found easily, for the yellow rectangle and for the orange one. For steady-state operation, these areas must be equal. As can be seen on Figure 4, and where D is a scalar called the duty cycle with a value between 0 and 1. This yields. From this equation, it can be seen that the output voltage of the converter varies linearly with the duty cycle for a given input voltage. As the duty cycle D is equal to the ratio between time and the period T, it cannot be more than 1. Therefore, this is why this converter is referred to as step-down converter. So, for example, stepping 12 of V down to 3 of E would require a duty cycle of 25%, in our theoretically ideal circuit. Discontinuous mode. In some cases, the amount of energy required by the load is too small. In this case, the current through the inductor falls to zero during part of the period. The only difference in the principle described above is that the inductor is completely discharged at the end of the commutation cycle. This has, however, some effect on the previous equations. We still consider that the converter operates in steady state. Therefore, the energy in the inductor is the same at the beginning and at the end of the cycle. This means that the average value of the inductor voltage is zero. That is, that the area of the yellow and orange rectangles in Figure 5 are the same. This yields. So the value of I is. The output current delivered to the load is constant, as we consider that the output capacitor is large enough to maintain a constant voltage across its terminals during a commutation cycle. This implies that the current flowing through the capacitor has a zero average value. Therefore, we have a. Where is the average value of the inductor current? As can be seen in Figure 5, the inductor current waveform has a triangular shape. Therefore, the average value of IL can be sorted out geometrically as follows. The inductor current is zero at the beginning and rises during turn up to Ilmax. That means that Ilmax is equal to. Substituting the value of Ilmax in the previous equation leads to. And substituting I by the expression given above yields. This expression can be rewritten as. It can be seen that the output voltage of a buck converter operating in discontinuous mode is much more complicated than its counterpart of the continuous mode. Furthermore, the output voltage is now a function not only of the input voltage and the duty cycle D, but also of the inductor value, the commutation period and the output current. From discontinuous to continuous mode. As mentioned at the beginning of this section, the converter operates in discontinuous mode when low current is drawn by the load, and in continuous mode at higher load current levels. The limit between discontinuous and continuous modes is reached when the inductor current falls to zero exactly at the end of the commutation cycle. Using the notations of Figure 5, this corresponds to. Therefore, the output current at the limit between discontinuous and continuous modes is. Substituting Ilmax by its value. On the limit between the two modes, the output voltage obeys both the expressions given respectively in the continuous and the discontinuous sections. In particular, the former is. So ILM can be written as. Let's now introduce two more notations, the normalized voltage, defined by. It is 0 when, and 1 when A. The normalized current, defined by. The term is equal to the maximum increase of the inductor current during a cycle. That is, the increase of the inductor current with a duty cycle D equals 1. So, in steady-state operation of the converter, this means that equals 0 for no output current, and 1 for the maximum current the converter can deliver. Using these notations, we have, in continuous mode. In discontinuous mode. The current at the limit between continuous and discontinuous mode is. Therefore, the locus of the limit between continuous and discontinuous modes is given by. These expressions have been plotted in Figure 6. From this, it is obvious that in continuous mode, the output voltage does only depend on the duty cycle, whereas it is far more complex in the discontinuous mode. This is important from a control point of view. Non-ideal circuit. The previous study was conducted with the following assumptions: the output capacitor has enough capacitance to supply power to the load without any noticeable variation in its voltage. The voltage drop across the diode when forward biased is zero, no commutation losses in the switch nor in the diode. These assumptions can be fairly far from reality, and the imperfections of the real components can have a detrimental effect on the operation of the converter. Output voltage ripple. Output voltage ripple is the name given to the phenomenon where the output voltage rises during the on state and falls during the off state. Several factors contribute to this including, but not limited to, switching frequency, output capacitance, inductor, load and any current limiting features of the control circuitry. At the most basic level the output voltage will rise and fall as a result of the output capacitor charging and discharging. During the off state, the current in this equation is the load current. In the on state, the current is the difference between the switch current and the load current. The duration of time is defined by the duty cycle and by the switching frequency. For the on state. For the off state. Qualitatively, as the output capacitor or switching frequency increase, the magnitude of the ripple decreases. Output voltage ripple is typically a design specification for the power supply and is selected based on several factors. Capacitor selection is normally determined based on cost, physical size and non-idealities of various capacitor types. Switching frequency selection is typically determined based on efficiency requirements, which tends to decrease at higher operating frequencies, as described below, and effects of non-ideality on the efficiency. Higher switching frequency can also reduce efficiency and possibly raise ME concerns. Output voltage ripple is one of the disadvantages of a switching power supply, and can also be a measure of its quality. Effects of non-ideality on the efficiency. A simplified analysis of the buck converter, as described above, does not account for non-idealities of the circuit components, nor does it account for the required control circuitry. Power losses due to the control circuitry are usually insignificant when compared with the losses in the power devices. The non-idealities of the power devices account for the bulk of the power losses in the converter. Both static and dynamic power losses occur in any switching regulator. Static power losses include losses in the wires or PCB traces, as well as in the switches and inductor, as in any electrical circuit. Dynamic power losses occur as a result of switching, such as the charging and discharging of the switch gate, and are proportional to the switching frequency. It is useful to begin by calculating the duty cycle for a non-ideal buck converter, which is where switch is the voltage drop on the power switch, VSYNCHSW is the voltage drop on the synchronous switch or diode, and VL is the voltage drop on the inductor. The voltage drops described above are all static power losses which are dependent primarily on DC current, and can therefore be easily calculated. For a transistor in saturation or a diode drop, switch and VSYNCHSW may already be known, based on the properties of the selected device. Where RON is the ON resistance of each switch, and RDCR is the DC resistance of the inductor. The duty cycle equation is somewhat recursive. A rough analysis can be made by first calculating the values of switch and VSYNCSW using the ideal duty cycle equation. Switch resistance, for components such as the power MOSFET, and forward voltage, for components such as the insulated gate bipolar transistor, can be determined by referring to data sheet specifications. In addition, power loss occurs as a result of leakage currents. This power loss is simply where I leakage is the leakage current of the switch, and V is the voltage across the switch. Dynamic power losses are due to the switching behavior of the selected pass devices. These losses include turn-on and turn-off switching losses and switch transition losses. Switch turn-on and turn-off losses are easily lumped together as where V is the voltage across the switch while the switch is off, tries and TFALL are the switch rise and fall times, and T is the switching period. But this doesn't take into account the parasitic capacitance of the MOSFET, which makes the Miller plate. Then, the switch losses will be more like when a MOSFET is used for the lower switch. Additional losses may occur during the time between the turn-off of the high-side switch and the turn-on of the low-side switch, when the body diode of the low-side MOSFET conducts the output current. This time, known as the non-overlap time, prevents shoot-through, a condition in which both switches are simultaneously turned on. The onset of shoot-through generates severe power loss and heat. Proper selection of non-overlap time must balance the risk of shoot-through with the increased power loss caused by conduction of the body diode. When a diode is used for the lower switch, diode forward turn-on time can reduce efficiency and lead to voltage overshoot. Power loss on the body diode is also proportional to switching frequency and is where VF is the forward voltage of the body diode, and TNO is the selected non-overlap time. Finally, power losses occur as a result of the power required to turn the switches on and off. For MOSFET switches, these losses are dominated by the gate charge, essentially the energy required to charge and discharge the capacitance of the MOSFET gate between the threshold voltage and the selected gate voltage. These switch transition losses occur primarily in the gate driver, and can be minimized by selecting MOSFETs with low gate charge, by driving the MOSFET gate to a lower voltage, or by operating at a lower frequency. Where Qg is the gate charge of the selected MOSFET, and VGS is the peak gate source voltage. It is essential to remember that, for NMOSFETs, the high side switch must be driven to a higher voltage than Vi. Therefore VG will nearly always be different for the high side and low side switches. A complete design for a buck converter includes a trade-off analysis of the various power losses. Designers balance these losses according to the expected uses of the finished design. A converter expected to have a low switching frequency does not require switches with low gate transition losses. A converter operating at a high duty cycle requires a low side switch with low conduction losses. Specific structures, synchronous rectification. A synchronous buck converter is a modified version of the basic buck converter circuit topology in which the diode, D, is replaced by a second switch, S2. This modification is a trade-off between increased cost and improved efficiency. In a standard buck converter, the flyback diode turns on its own, shortly after the switch turns off, as a result of the rising voltage across the diode. This voltage drop across the diode results in a power loss which is equal to where Vd is the voltage drop across the diode at the load current IO, D is the duty cycle, and IO is the load current. By replacing diode D with switch S2, which is advantageously selected for low losses, the converter efficiency can be improved. For example, a MOSFET with very low RDSON might be selected for S2, providing power loss on switch 2 which is. In both cases, power loss is strongly dependent on the duty cycle. D power loss on the freewheeling diode or lower switch will be proportional to its on time. Therefore, systems designed for low duty cycle operation will suffer from higher losses in the freewheeling diode or lower switch, and for such systems it is advantageous to consider a synchronous buck converter design. Without actual numbers, the reader will find the usefulness of this substitution to be unclear. Consider a computer power supply, where the input is 5 V, the output is 3.3 V, and the load current is 10 A. In this case, the duty cycle will be 66% and the diode would be on for 34% of the time. A typical diode with forward voltage of 0.7 V would suffer a power loss of 2.38 to WA. Well-selected MOSFET with RDSON of 0.015 AI copyright, however, would waste only 0.51 AW in conduction loss. This translates to improved efficiency and reduced heat loss. Another advantage of the synchronous converter is that it is bidirectional, which lends itself to applications requiring regenerative braking. When power is transferred in the reverse direction, it acts much like a boost converter. The advantages of the synchronous buck converter do not come without cost. First, the lower switch typically costs more than the freewheeling diode. Second, the complexity of the converter is vastly increased due to the need for a complementary output switch driver. Such a driver must prevent both switches from being turned on at the same time, a fault known as shoch-through. The simplest technique for avoiding shoch-through is a time delay between the turn-off of S1 to the turn-on of S2, and vice versa. However, setting this time delay long enough to ensure that S1 and S2 are never both on will itself result in excess power loss. An improved technique for preventing this condition is known as adaptive non-overlap protection, in which the voltage at the switch node is sensed to determine its state. When the switch node voltage passes a preset threshold, the time delay is started. The driver can thus adjust to many types of switches without the excessive power loss this flexibility would cause with a fixed non-overlap time. Multiphase buck. The multiphase buck converter is circuit topology where the basic buck converter circuit are placed in parallel between the input and load. Each of the N phases is turned on at equally spaced intervals over the switching period. This circuit is typically used with the synchronous buck topology, described above. The primary advantage of this type of converter is that it can respond to load changes as quickly as if it switched at n times as fast, without the increase in switching losses that would cause. Thus, it can respond to rapidly changing loads, such as modern microprocessors. There is also a significant decrease in switching ripple. Not only is there the decrease due to the increased effective frequency, but any time that n times the duty cycle is an integer, the switching ripple goes to zero. The rate at which the inductor current is increasing in the phases which are switched on exactly matches the rate at which it is decreasing in the phases which are switched off. Another advantage is that the load current is split among the n phases of the multiphase converter. This load splitting allows the heat losses on each of the switches to be spread across a larger area. This circuit topology is used in computer power supplies to convert the 12V DC power supply to a lower voltage, suitable for the CPU. Modern CPU power requirements can exceed 200 W, can change very rapidly, and have very tight ripple requirements, less than 10 megavolts. Typical motherboard power supplies use 3 or 4 phases, although control IC manufacturers allow as many as 6 phases. One major challenge inherent in the multiphase converter is ensuring the load current is balanced evenly across the n phases. This current balancing can be performed in a number of ways. Current can be measured losslessly by sensing the voltage across the inductor or the lower switch. This technique is considered lossless because it relies on resistive losses inherent in the buck converter topology. Another technique is to insert a small resistor in the circuit and measure the voltage across it. This approach is more accurate and adjustable, but incurs several costs: space, efficiency and money. Finally, the current can be measured at the input. Voltage can be measured losslessly, across the upper switch, or using a power resistor, to approximate the current being drawn. This approach is technically more challenging, since switching noise cannot be easily filtered out. However, it is less expensive than emplacing a sense resistor for each phase. Efficiency factors: conduction losses that depend on load, resistance when the transistor or MOSFET switch is conducting. Diode forward voltage drop, inductor winding resistance, capacitor equivalent series resistance, switching losses, voltage ampere overlap loss, frequency switch CV2 loss, reverse latence loss, losses due driving MOSFET gate and controller consumption. Transistor leakage current losses, and controller standby consumption. Impedance matching: a buck converter can be used to maximize the power transfer through the use of impedance matching. An application of this is in a maximum power point tracker commonly used in photovoltaic systems. By the equation for electric power, where VO is the output voltage, IO is the output current, I is the power efficiency, Vi is the input voltage, E is the input current, by Ohm's law. Where ZO is the output's impedance, Xi is the input's impedance, substituting these expressions for IO and E into the power equation yields. As was previously shown for the continuous mode. Where D is the duty cycle, substituting this equation for VO into the previous equation, yields, which reduces to. And finally, this shows that it is possible to adjust the impedance ratio by adjusting the duty cycle. This is particularly useful in applications where the impedance, S, are dynamically changing. See also, boost converter, buck boost converter, split pi, general DC-DC converters and switched mode power supplies. References: P. Julia N., A. Oliva, P. Mandlesi, and H. Kyakurinai, a OE output discrete feedback control of a DC-DC buck converter, a and Proceedings of the IEEE International Symposium on Industrial Electronics, Guimarães, Portugal, 7-11 Julio 1997, ppA 925 a 930. H. Kyakurinai, P. Mandlesi, A. Oliva, and P. Julia N., a OE nonlinear analog controller for a buck converter, theory and experimental results. A Proceedings of the IEEE International Symposium on Industrial Electronics, Bled, Slovenia, 12 Euro July 16, 1999, ppA 601 Euro 606. MB da Euro Unregistered Trademark Amico, A Aliva, EE Paolini y Engaran, a Euro OE bifurcation control of a buck converter in discontinuous conduction mode a Euro. Proceedings of the first IFAC Conference on Analysis and Control of Chaotic Systems, ppA 399 a Euro 404, Reims, 28 L30 de Junio de 2006. Aliva, AR, H. Kyakurin IYG Bortolotto a Euro OE developing of a state feedback controller for the synchronous buck converter a Euro, Latin American Applied Research, Volume 35, NRO2, April 2005, ppA 83 a Euro 88. ISSN, 0327-0793. Da Euro Unregistered Trademark Amico, MB, Garan, N, Aliva, AR, Paolini, EE Dinamica di Unconverted or Buck Concontrolled or PI Digital. Revista Ibero-Americana de Automática e Informática Industrial, Vol. 4, No. 3, Julio 2007, ppA 126 a Euro 131. ISSN, 1697-7912. Ciacci, F. Paolini, EE Discrete Time Modeling and Control of a Synchronous Buck Converter Argentine School of Micro-Nanoelectronics, Technology and Applications, 2009. EAMTA 2009.1 a Euro October 2, 2009, ppA 5 a Euro 10. ISBN 978-1-4244-4835-7. External links. Interactive Power Electronics Seminar. Many Java applets demonstrating the operation of converters, model-based control of digital buck converter description and working BISIM source code diagram for low-cost digital control of DC-DC buck converters, SPI simulation of the buck converter, switch mode power supply tutorial, detailed article on DC-DC converters which gives a more formal and detailed analysis of the buck including the effects of nonideal switching. DC-DC power converter case study, on the power efficiency optimization.